We spend every moment of our lives surrounded by sound, from the hum of a passing car to the gentle whistle of the wind, or even the voice of someone we love. But how exactly do we perceive the volume, pitch, and even the direction of these sounds? What if we were in an environment completely different from Earth? On Mars, for example, would we still hear things the same way we do here? It's a question you've probably wondered about at least once. So, in today's Dr. SciVera studio, we're going to take a closer look at how humans detect sound and how that ability might change in environments beyond our own. Alright, let's get started. Need to start with a simple question. What exactly is sound? At its core, sound is created by vibrations. When an object vibrates, it pushes and pulls on the surrounding material, creating waves that travel through it. And here's the key. Sound cannot exist without something to carry it. It needs a medium. That's why in the vacuum of space, no matter how loudly you shout, there's nothing to transmit those vibrations, and sound simply doesn't travel. So how do we actually detect these waves? It all starts with our ears. When sound waves enter the ear, they cause the eardrum to vibrate. Those vibrations are passed into the inner ear, where they're converted into electrical signals. These signals then travel along the auditory nerve to the brain. From there, the brain puts everything together, interpreting the loudness, pitch, timbre, and even the direction of the sound. In that tiny fraction of a second, an incredibly complex process is unfolding inside your body. Now here's something interesting. Have you ever wondered how we can pinpoint exactly where a sound is coming from? The way our body does this is actually quite remarkable. We determine the direction of a sound by combining two key pieces of information. First, there's a timing difference. If a sound comes from your right ear hears it slightly earlier than your left. The gap is incredibly small, on the order of microseconds, but the human brain is sensitive enough to detect even these tiny differences. Second, there's a difference in intensity or sound pressure. When a sound comes from the right, your head acts as a barrier, causing the sound reaching your left ear to be slightly weaker. The brain combines both of these cues to determine where the sound is coming from. Neither cue is sufficient on its own, so it relies on both together. Interestingly, this is not unique to humans. Almost all land animals use the same mechanism. It's truly one of the remarkable features of nature. Now here's another question. Between a low-frequency hum and a high-pitched ringing sound, which one do you think is easier to locate? If both sounds have the same loudness, the high-frequency sound is actually easier to pinpoint. But why is that? It all comes down to how sound waves interact with obstacles. When a sound wave encounters an obstacle, it doesn't just stop, it can actually bend around it and keep going. But for this to happen effectively, the wavelength needs to be longer than the size of the obstacle. That's why low-frequency sounds with their longer wavelengths can easily wrap around your head. On the other hand, as wavelengths get shorter, meaning higher frequencies, the waves become much more directional. They travel in a straighter line and struggle to bend around obstacles. This is closely related to ultrasound, which I've covered before, so if you're interested, you can check the link in the top right corner. Applying this to our case, high-frequency sounds with wavelengths shorter than the width of your head cannot easily travel around to the far ear. This creates what we call a sound shadow on the opposite side of your head, where the waves struggle to reach. As a result, these high-frequency sounds are significantly weakened by the time they reach the other ear, creating a clear difference in intensity between the two ears. Because of this, the brain can pinpoint the direction of the sound with much greater clarity. On the other hand, low-frequency sounds have much longer wavelengths. These waves can easily wrap around the head, much like water flowing around an obstacle. Because they reach both ears with nearly the same intensity, the difference between them is minimal, making it much harder for the brain to determine where the sound is coming from. This principle shows up in some interesting ways in our everyday lives. For example, do you use a sound system with a separate subwoofer? We often feel like the ideal setup is to place everything right in the center, but in reality, whether it's for a TV or a PC, it's often impractical to position a subwoofer in the middle. At the same time, placing it off to one side can feel a bit uncomfortable, as if the sound might be slightly lopsided. But from a scientific point of view, there's actually no problem at all. Subwoofers typically handle frequencies between 20 and 200 Hz. At this range, the wavelengths span roughly from about 1.7 meters to around 17 meters. These waves are far larger than the size of your head, or even most objects in a room. Because of this, such long wavelengths are not significantly affected by obstacles and can easily bend around them, meaning there is almost no difference in the sound reaching each ear. As a result, the sound becomes effectively non-directional, so whether the subwoofer is placed in a corner, against a wall, or elsewhere, most people cannot localize its exact position. Of course, sound reflections within a room can still have an effect, and for people who are highly sensitive to sound or for audio professionals, the experience may be different. In any case, the key point is that low-frequency sounds are less affected by obstacles, while high-frequency sounds are affected much more. And for the same reason, when you are in a car or at home, it is often difficult to pinpoint the source of low-frequency humming noises. So, let's return to our original question. If we were standing on the surface of Mars, would sound reach our ears the same way it does here on Earth? Remember, sound needs a medium to travel, and that's exactly what the atmosphere does. Earth's atmosphere is mostly nitrogen and oxygen. Even in a tiny space like just 1 milliliter, there are about 25 quintillion gas molecules. Mars, on the other hand, has an atmosphere made mostly of carbon dioxide, and its surface pressure is only about 0.6% of Earth's. That makes it extremely thin. Because the density of the medium is so low, sound doesn't travel nearly as well on Mars as it does on Earth. Also, as sound travels, it loses energy much faster. This means that on Mars, sound struggles to travel long distances and quickly fades away, even over short distances. But there's another key factor. Carbon dioxide molecules aren't simple. They have internal ways of vibrating and rotating. When high-pitched sounds pass through, they interact strongly with these motions and lose their energy quickly. Think of it like a filter. On Mars, high-pitched sounds fade away almost instantly, while low-pitched sounds travel a bit further. This leaves the audio sounding muffled and distorted, unlike anything we hear on Earth. Now, aren't you curious about how sound actually changes on Mars? The sound you're about to hear was recorded by a NASA Mars rover. Take a listen and see if you can guess what's making this sound. What do you think? To me, it sounds a bit like a small distant motorcycle, but in reality, it's the sound of Ingenuity, the Mars helicopter. Now let's compare that to how a drone sounds here on Earth. If you listen closely, you'll notice that on Mars, the high-pitched whir of the drone is significantly reduced, leaving a more muffled, dull sound. In other words, the Martian atmosphere filters out the higher frequencies, creating noticeable distortion compared to what we hear on Earth. Even so, the sound itself can still reach our ears. The real kicker is pinpointing where that sound is coming from. On Mars, it would still be possible to estimate direction to some extent, using the timing difference between when the sound reaches each ear. However, relying on differences in intensity or sound pressure becomes much more difficult. Because high-frequency sound waves lose energy rapidly in the thin carbon dioxide atmosphere, by the time they reach our ears, they are already too weak for the head to create a clear sound shadow. Without that difference in intensity, it becomes much harder for the brain to determine the direction of high-frequency sounds unless the source is very close. The situation is equally challenging for low-frequency sounds. As we discussed earlier, low-frequency waves have long wavelengths and easily wrap around the head, which already makes them difficult to localize. In conclusion, whether the sound is high-frequency or low-frequency, identifying its direction on Mars would be significantly more difficult. In addition, due to frequency-dependent distortion, sounds on Mars would be perceived quite differently from those on Earth. Today, we explored how we perceive sound and whether that experience would carry over to a completely different environment like Mars. As we've seen, the human auditory system is far more complex and sophisticated than we often realize. What started as a simple curiosity led us through the physics of sound waves, the mechanics of hearing, and how our environment fundamentally shapes the way we perceive sound. To me, this is where the true power of science and engineering lies, in how a small question can lead to new discoveries and real-world applications. If there's a topic you're curious about, feel free to leave a comment anytime. We'll wrap up here for today, and I'll see you again next time with another interesting topic. This has been Dr. SciVera.